Uh, yes. So the title for today's talk is Abelian groups, the unbuilding blocks. The basic idea of the talk is that we will be discussing how the fundamental theorem of finitely generated Abelian groups is essentially, if we remove one condition from it, that is for the rank to be greater than zero, we make it rank equal to zero. It essentially becomes the fundamental theorem for the finite Abelian groups. So let's move ahead with that. We will just be developing the intuition for it through some examples. We will not very rigorously prove it. Okay. Yes. So this is the outline. Yeah, that's a quote from Dostoevsky. So the fundamental theorem of finitely generated Abelian groups, a breakdown. The theorem states that let G be a finitely generated Abelian group, then G is isomorphic to a direct sum of cyclic groups. Denoted as that, where z to the power n, which is zn, is the free, we'll be saying it zn. We should not confuse it with the other notation, which is z and z. Here, zn is the free abelian group of rank n greater than equal to zero. If it becomes equal to zero, then the part vanishes because it becomes the trivial group itself. The number of infinite components, ZQi or the power Ki, are finite cyclic groups of prime power order Qi Ki, where Qi is a prime and Ki are the powers of the prime. Uh, the uniqueness part of the theorem states that the rank n is uniquely determined and the prime powers called the elementary divisors are uniquely determined up to the ordering. That is, if we change the ordering, then the isomorphism of the group G will not be affected. Uh, to understand the theorem, let's first visit a few necessary terms that we must know in order to grasp the concept of the theorem. The first we have the idea of the free abelian group. So a free abelian group is an abelian group. Abelian, for those who do not really know what that means, is that you take a group, but then you imply another condition on it, and let's say an additional condition on it, which establishes the commutativity of the elements of the group. That is, if we have two elements, A and B, belonging to a group G, then the group operation performed on AB uh, and the group operation performed on BA, that is, in those specific orders, will result in the same element of the group. Now, the free abelian group is an abelian group that has a basis. Uh, we might be familiar with the linear algebra, right? So the concept of basis can is analogous to that here too. There exists a subset called a basis. Now the subset is of the free abelian group itself, such that every element of the group can be uniquely expressed as a finite linear combination of the basis elements with integer coefficients. And the rank of a free abelian group is the cardinality of a basis. The intuitive idea to grasp the concept of rank can be developed from considering it as the number of independent directions that a particle or an element of a group is allowed to move in, which in the case of a free group are infinite, since a free group is essentially free. So the concept of a free group is that we do not really have any external condition imposed on it. Let's define free group. Consider S to be a set. We are not imposing it to be an empty or a non-empty set. Let S just be a set. Then the free group, that is F of S. So we are defining a group on S, which is we generate a group F of S from the elements of the set S, consists of all the reduced words. Consists of one sec. Consists of all the reduced words in S union S inverse. These are the simple notations as we follow in set theory and others, where a word is reduced if no element is adjacent to its inverse. Which means that suppose we have an element A in S and an element B in S. Since we are constructing a group, we also take their inverses to be in S. F of S. A and B are in S, so A, B, A inverse and B inverse will exist in F of S. Now, suppose we are performing the operation on the elements written in this format. This is a very trivial example. So here we are writing that consists of all the reduced words in S union S inverse. Reduced, here we said that no element is adjacent to its inverse. So B inverse essentially becomes the identity, and we have E, A inverse. And identity, we know that it results into the same element. So we have A inverse, and then we again apply the same condition which says that no element is adjacent to its inverse. So this again becomes E. That is the concept of the free groups operations. Multiplication is concatenation followed by reduction. Reduction, as I have mentioned already, it satisfies the universal property. And any function defined, say, from the set S on a group G extends uniquely to a homomorphism. That is, we can define a unique homomorphism from the free group of set S onto the group G. Moving ahead. Universal property. This is essentially the same thing stated again. There's one line we must note which says that freedom to map without relations getting in the way. That is, the homomorphism does not restrict the relations of the free group in any manner. Let's see an example. Suppose we have taken two elements A and B from the underlying set S, and we have mapped it to the group S3, which is the symmetric group S3, with order 6. We have taken f of A as 1, 2, sorry, 1, 2 as the cycle, and f of B as 1, 2, and 3, which are arbitrary choices. We can take any two other elements which can help us generate S3. So phi, the map we have defined as phi of AB will be FA, FB. How does that work? We have defined it as that, and we know that the homomorphism follows the rule that phi AB will be phi A and phi of B. So when we work out these calculations, it essentially becomes this, and we can define different homomorphisms which are unique to the structure of the group in the similar format. To see the computation, the generators, the f of AB has f a comma b has no relations. Words like AB and BA are distinct. And phi substitutes generators and simplifies in S3, as we have mentioned already, that this will essentially turn into the operations of the group itself, and it would again result into the element of S3. To check the verification, we can just, to verify, we can simply check the condition for homomorphism. Now, a free abelian group. An abelian group with a basis B subset of G. We had defined a free abelian group before this too, and we had mentioned that it must have a basis B, which is a subset of the group itself, such that B generates G and the linear independence property holds. That is, we can express an element of G in the form of a linear combination of the elements of B with integer coefficients. And if this is 0, this implies that the coefficients are 0. Isomorphic to Zn for finite rank n, where n has to be finite. And uniqueness. Uniqueness implies that if summation of ni bi is equal to summation of mi bi for some ni's and some bi's, then ni must be equal to mi for each I in the indexing set I. Okay. Let's see an example. Z2 with the basis 1, 0 and 0, 1. We have this as the basis of Z2, and this also generates the entire Z2. Please do not confuse it with Z and Z. It's Z cross Z. A non-example would be Z and Z. Here we will not really be able to find, it is not a free abelian group. It is a abelian group, but it will, we will not be able to, this is an infinite abelian group. We will not be able to find a finite basis for it.
Yeah, because of the torsion, right?
Yes, because of that.
So when you have an element,
Is that a sufficient condition? Sorry.
Right. Yes, when you have an element, can you hear me?
Yes, I can.
When you have an element and when it is multiplied by a non-zero divisor and when it gives to zero, it is not merely showing the linear independence. So there's some sort of torsion
Yes.
in these groups because there are these modulos. Uh, so you do not have a
Yes, yes,
free
yes.
basis. That's why you cannot say it has a basis. That's why when you yeah something else right go on.
Yes, yes, thank you. Yes, and the word torsion comes from the Latin verb to twist, like twisting a rope until it moves back. Uh, we will define torsion subgroups later, so we'll come back to this and we'll understand this better. Just for reference, let's define the direct and direct products and things too for proving or understanding the theorem. We have the direct external product defined as h cross k such that h comma k, where h is taken from the subgroup H of G and K, the element K is taken from the subgroup K of G with component wise operations applied. And then we have direct sum, which is for abelian groups, it is the same as H cross K. And the internal direct products, where a group G can be uh, expressed as the internal direct product of H and K being its normal subgroups if each element in G can be expressed in a unique way in the form HK, where H belongs to the normal subgroup H and K belongs to the normal subgroup K. External constructs new groups from old and internal decomposes the existing groups into simpler pieces. As we can see that in the external case, we are actually constructing a group, and in the internal case, we have just taken the normal subgroups and we are expressing the group that we had in the form of the operations applied on the normal subgroups. Okay, now the fundamental theorem. Every finitely generated abelian group G decomposes as G isomorphic to ZR, where this is the free part of the free part, and Z D1, so on until Z dk, which is where these are the torsion parts. Now R greater than equal to, when the equal to condition also applies, this becomes the fundamental theorem. The emphasis on the implies that this will cover the finitely generated abelian groups as well as the finite abelian groups or the abelian groups like that. We have R greater than 0 for finitely generated abelian groups and Di greater than 1. We need, of course, we need them to be greater than 1. Otherwise, with 1, it definitely divides all the other numbers with such that dk minus 1 divides dk, where dk's are all primes, or di's, we must say, are all primes. We have, let's see an example. We have G into Z2 and Z6 into Z2 and Z3. And we divided Z30 into Z2, Z3, and Z5. Yes. And so that we have D1 as 2 to the power 1 for, one second, for these. We have D1 as 2 to the power 1, 3 to the power 1, and 5 to the power 0. Since there is no component of zeros, we get 6 for the first one. And then for the second part of it, we have 2 to the power 1, 3 to the power 1, and 5 to the power 1 taken from this, which results into 30. Now, since 6 divides 30, we can express it as the direct product of these. We must have written it like this. Sorry for that. Yes. Moving ahead. Yes. Coming to torsion subgroup. For an abelian group G, the torsion group of G is defined as is a collection of all the elements in G such that uh, for a positive integer n, which is finite, g to the power n would be e. What it means is that, in the simplest terms, it consists of all the elements of the group which have a finite order. Uh, Consider the example. We have G equal to Z with Z6. Then the torsion group of G would be essentially Z6, but we can also write it as this. Here, here we can denote the trivial group as this 2, where this becomes 0 for us, and hence the free part is the trivial group. Moving ahead, now we have torsion-free groups. G is torsion-free if the only element with a finite order which results in the identity is the identity itself. That is pretty self-explanatory. That is, if we cannot find any other element in the group G such that it would result in the identity, that is, all the other elements are of infinite order, then the torsion the torsion subgroup of the group would be the trivial subgroup. Examples can be Zn. In Zn, with the in Zn with the operation of addition, we have the torsion subgroup to be the identity, and same goes with the group of rationals. And non-example would be Z and Z. We have seen that it is a torsion-free. Wait, yes, it would be Z and Z. Again, the case of the modulo applies.
How are you defining torsion subgroup to be those elements which have finite order? Can't you define it like those elements when multiplied by some sort of non-zero divisors yields zero? Isn't that torsion? And a torsion free means yeah.
No, I think this is the right definition. I think this is how it is defined. It consists of all the elements of the group which have a finite order, which will
Finite
revert back
order.
to the identity. Yes.
Not sure. Not sure. I'm not sure. It's not how a torsion is generally defined. Torsion is defined as those elements. So you understand what is a non-zero divisor. And a non-zero divisor, see, a zero
Yes, yes,
divisor is just
yes.
zero, right? A
Yes.
zero divisor is a zero. Like let's say something is a zero divisor. So that means it will take an element to zero. For example, zero is a zero divisor, right? So if I multiply 4 with zero, it gets zero. But if you have non-zero divisors and still you multiply it with some sort of element which gets to zero, then that specific element, not the zero divisor, not non-zero divisor, but the element which is getting multiplied is called the torsion element, right?
I understand what you're talking about. Like, if we take Z5 and say we have I don't know, an element, let's say,
5
mm,
cross 1, right? 5 cross 1. Let's say that is
mm,
your,
this.
what is it? Under modulo 5,
No, what did you? Then that would be 0.
right? So 5 is non-zero a non-zero divisor. One is a non-zero divisor, but still it is going to zero. That means this
Results in
group is
0. Yes. Yes.
that results in zero. So what you see is 5 and 1 are basically torsion element. And if in Z5, nothing like this would have happened, then we would have called Z5 a torsion-free group. So Z and are never torsion-free. They always have a torsion subgroup. Subgroup. That's why you say
Oh,
it
that
is
is
in a
why it is a
non-example.
non-example, no? Yes.
Yes, but I'm saying your definition is not really of torsion. I think this is not how it is defined. Actually,
Oh, so you're asking me it's supposed to be this, and then something like NG goes to E. This?
Yeah, right. But I think this is not how it is defined, is it? Anyway, you go ahead.
The way I have written it,
Yeah, yeah.
the
Is it
way
how
I
it is
have written,
defined? Isn't it definition of just finite elements, right? Maybe. Go on.
yes, but the definition of the torsion subgroup gives this idea as what it should be, and this relates more to, doesn't it relate more to the, say, when we talk about rings and things, because
No,
that is where zero devices come into play, don't they?
no. Yeah, no, it's okay. Even in Z5 under a multiplication modulo or zero divisor should come. It's okay. I'm not sure where did you pick this definition from. Let's move on. Maybe you must have something to do with this definition, right?
For now, I think that would have a better and more
Yeah, yeah, yeah.
say,
Yeah, I
yeah,
think this
in
definition also
between when it
exists.
comes to rings. Yeah.
No, not
Okay.
necessarily. Not necessarily. It's in linear algebra. What I gave you is a definition in linear algebra. When you discuss modules and stuff, not rings. Anyway, you go move on. I think this definition is right. I was not sure uh, if I connected these two definitions earlier. Yeah, sorry. Go on.
See, this could be wrong too. I am not saying that. This could be wrong because this I had written, this is what I understood from the definition. This is not what they had written as a
No,
set,
I think,
set in
see,
it.
now I can make sense of it. Both of these are similar definitions. I will tell you later. Okay.
Similar. Yeah,
Yeah.
yes.
Graceland. Yes, you may resume.
Yeah. So we will see a few examples based on the parts of the proof. There are a few theorems that we must be well versed with in order to prove the fundamental theorem. The first one is that if G is finitely generated Abelian group, then P of G is a finite subgroup. We
Just to
have
just to be just to be very basic, finitely generated just means you have a finitely generated set, right? Whatever this abelian group is being generated, that has finite number of elements. That is what you mean by finitely generated.
mean that the group is finitely generated as. What did you say? Can you repeat that?
See, finitely generated would typically mean that you have a generating set and that has finitely number of elements in it, right?
Yes, yes, exactly. Yes,
You are
exactly.
meaning here.
Yeah. So T of G is a finite subgroup, and when we form the quotient group, uh, with respect to the torsion subgroup, then it is torsion free and finitely generated. Uh, we will look at it with some examples, but it is also easy to understand from here that since we have factored out it in the form of the torsion subgroups, we're using a torsion subgroup, then what we are left with is a torsion free part of the group. Uh, and since this is torsion free, so it is free abelian. We had seen that in the theorem itself that it says that we have the free part and then we have the torsion part. So moving ahead, let's see a few examples. Let's say there's a group G, which we have as Z cross Z2. Uh, the torsion part of the group Z would just be E, and that of the Z2Z would be, uh, this is, we have seen here that a group of the form Z and Z will not be a torsion free group. So this is a torsion subgroup of itself, and then we have it. So if we factor out in terms of the torsion subgroup of the group G, we obtain, say if we factor out in terms of E, we just get the group itself, and then okay, wait, maybe let's work this out. we ob- yeah, yeah, yeah. We obtain this by factoring out, sorry, by obtaining the torsion subgroup. And then if we do this, that is, we with the operation, and then we have the torsion part would essentially form, one second. Torsion part would essentially form E, comma, Z to Z has elements of the form, comma, 0, and then we have 0, comma, 1. Is this like, would it not generate Z? Are we missing something here?
No, no, see, if I may draw here,
Yes.
just
Do you have the permission?
of course, I started
I
the
think
meeting.
you do. Yeah.
Okay, so see,
Mhm.
in Z, what happens is the only element which gets mapped to zero is zero, right?
Yours
Zero
vanishes.
multiple.
Yours
Yeah, yeah.
vanishes.
Haha, I know, for a reason. Okay, you don't want the vanishing, right? Okay. So if you have a zero cross M, this is zero, right? And this is a non-zero divisor.
Yes.
Non-zero divisor means what? Like that means what? N by M will not equal to zero, right?
Mm-hmm.
Right? So what
Mm-hmm.
happens now, the only element to go through to zero in Z is zero only. So the torsion here is just zero. That's why you have written it zero. But in Z2, the whole torsion group, okay, what just happens? The whole torsion is Z to Z. Because see, even for one, you have torsion. For two, you have torsion, right? How? Uh, 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 what is this group under? Like plus or multiplication?
It's under plus.
Yeah, so you can send it to zero, right? Every element can be sent to
Yes.
zero, right? For example, one can be sent to zero. How?
Mhm.
It can be sent zero by adding by one. Like what happens? Just doesn't draw. Anyway, one goes to one plus one goes to zero, right? Even though
Yes,
one is a
yes.
non-zero and one is not zero, two can also be taken to zero, right? Two plus zero is equal to two, and that is torsion. So the whole torsion subgroup of this group is zero across the whole group. And when you take the quotient, what you should get something like that, right? You should get something which is a torsion free. And this is actually a torsion free, right? Zn is torsion free. So this is just Z1. So this example is right. You were doing right. Just delete everything now. Yeah, sorry. So
No, so yeah, what I wrote as a torsion subgroup was also right?
yeah, it's right. Zero cross.
Yeah, this is the torsion. Yes. No, but
Not
if we,
exactly
this is,
this.
since we're,
Oh yeah. Okay, you are doing the product.
this is it, right? Yeah.
Ha. Yeah. You opened the product. It's okay. So
Yes, yes.
when you
I
take the
listed the
question, it
elements.
should be when you take the question, it should become a torsion free group, and that is exactly Z. Okay, go on.
Okay. Again, to begin with, Uh, this, yes, again, to begin with, we can, of course, write it like this. This is how generally it is mentioned. But I prefer this when you talk of the order of the element. I prefer this notation rather than this one. Okay. And now with that being mentioned, let's see, the P primary component, that is the torsion P subgroup, would be for some prime P, G belonging to this would be elements of the form such that G in TG has a, one second, G in TG has a prime order, uh, or we can also say that, sorry, or we can also say that this doesn't necessarily, yeah, sorry. We can also say that this doesn't necessarily mean that p to the power k is the order of G. This also means that if the order of G is, say, m, then m divides p to the power k. Okay. This is what it means actually. Just saying it directly that this is p to the power k is the order of G would be wrong. Okay. So this, let's move ahead with this. So this is this is another subgroup that we can generate from the torsion subgroup of G, consisting of all the elements of the group G, such that they result in the identity when raised to a prime power, say P. Okay. We can also perform the prime decomposition by writing it as the direct sum, sorry, of all the torsion P subgroups. Say we have a group T of G. Yeah, we have a group, the torsion group, where we have it as Z6Z, and then it can be decomposed as Z2 cross Z3, and in case of Z2, Z2 itself is the torsion subgroup. And in case of Z3, Z3 itself is the torsion subgroup. It is also the torsion P subgroup where P is 2 in this case and and P is 3 in this case. Now the fundamental theorem for finite abelian groups. Sorry for the spelling. Yeah. A finite abelian P group decomposes as this. We have also done it in MLS, I think. I had mentioned this. Say H is a finite abelian group. P group just means that it has a prime, it has its order is prime or a power of prime, okay, of the form p to the power k, let's say. Then it can be decomposed in the form this, where E1 is less than or equal to E2 and so on until EK, which means that say we have, yeah, yeah, say we have a group of order, I don't know, say 8. Okay, then we can decompose it in the form of Z2 cross Z2 like this. We can also write it like this. There's no problem with that. But yes, those are not the only decompositions that would exist. Let's consider an example. We have a torsion subgroup Z2 cross Z4 cross Z3 and Z9. The torsion 2 subgroup, we are performing the primary decomposition would be for for this part would be Z2, and then we have Z4, which is Z2 once to the power 1 I have written. That is the power 1. And then this is this. Similarly, for this, we have Z3Z as Z3 to the power 1Z cross Z9Z. 9 is to the power 3 to the power 2. So we can write it like that. When we exponent it by the prime, yeah, sorry, we have the components. So in T2, we have 1 and 2 as the powers of 2. And in 3, we have 1 and 2 again. So we form the invariant factors where we take the minimum and the maximum. So we get 6 and 36. So essentially, the torsion group of G would be isomorphic to Z6Z and Z36Z, the direct products of Z6Z and Z36Z. That is what the theorem that we had stated earlier tells us. Dissecting the theorem that we had stated, which we call the fundamental theorem, where we had a free part and a torsion part. Uh, okay, so the torsion part, as we have already discussed previous to this, it is that we have an element such that we perform the operation, say back to back on it, and then it comes back to the identity or comes back to the same point. Uh, See, we are traveling in a circular path, and we start at a point A. One sec. We are traveling in a circular path. Suppose we start here. Then we end up, if we keep traveling as the path directs us, we end up here again. So this is the intuition behind the word torsion here. Okay. With this, d greater than 1, we can also write it as d k minus 1 divides d of k, as I had mentioned in the theorem. Moving ahead. Yes, so R, as I said, that rank can be simply understood as the free, as the independent dimensions, say that a particle is allowed to move in. And then we have these, which instead of this, we can just look here, and that would be understandable. Another example would be if we take z cross z, and then we have its direct product with z4. The free part, rank is 2, as we can see, and the torsion group is z4z, where d1 is 4. D1, yes. If we compare this, do you see if I highlight it like this? Is this visible?
Yes, yes.
Yeah. So if we compare this with what is given here, we see that R is 2 here and D1 is 4 here. This is essentially what we have stated, and the decomposition is written exactly like that. We have already addressed this since the beginning. What if the free part has the rank 0? Then the theorem is referred to as the fundamental theorem of finite Abelian groups rather than the fundamental theorem of the finitely generated Abelian groups. This was the point of having this talk, just to show that the fundamental theorem of finite Abelian groups is a special case where rank is equal to 0 uh, when we talk about the fundamental theorem for finitely generated Abelian groups. This is the for the Abelian groups, as we see that the free part, like the free part is not mentioned here now, because the rank has become 0. Uh, yes, that's understandable that the rearrangement of the prime powers. We can of course play around with, say, if we have written z2 cross z3, we can also write it as z3 cross z2. It wouldn't really change, say, the structure of the group. It would definitely change the notation of the elements. PIs, that is the primes, are not necessarily supposed to be distinct. And of course, the powers of the primes must be positive integers. Just as Z6 decomposes into Z2 with the direct product with Z3. So that was it. I'm sorry for the confusions, of course, Jenny. But yes, the essential idea was just to show that we can develop the intuition for the fundamental theorem for finitely generated Abelian groups by just proving or understanding the fundamental theorem of finite Abelian groups, or vice versa, whichever comes more natural to one first. Yes. Thank you.
But just a simple comment. Whenever you talk about finitely generated and finite groups, see, these have more I think these are more in linear algebra than they are in groups. I have felt so far. And these things are very nice things, by the way. Good. Yeah, if there are
Yes,
no
I found
questions.
it to be very good how like I had not really noticed that those are two different things for me because it came to be very natural. But then when I noticed it that the free part is missing, and then I thought it's something to be talked about and to be, the people must just know not everything has to have the goal to it assigned to it, right?